Hello, Stats 300. This is Professor Gonzalez, and we're taking a look at the homework problems, two homework problems from section 8.2 on the assignment side of ALEKS. And then I'm also going to do 8.2 on the interactive side, which is one more problem. So we have three more problems. And then I would have, at that point, I will have done all the homework problems on the interactive and assignment side of ALEKS for you and made videos. On this one, what I'd like to do before we start this problem is do a little mini lecture on 8.2, which would cover my take on 8.2. So this is section 8.2. And let's just start by saying suppose. So suppose we're about to draw a random or a simple random sample of n observations from a normally distributed population. Okay, so in this situation, right, we would use z-scores. Right, we'd have our sample mean minus our population mean divided by our standard deviation of these sample means. And just to highlight, of course, here's the numerator again. But to highlight something here, this denominator is equal to the standard deviation divided by the square root of n. The point is, when we use this formula, we need to know our standard deviation, and that's from the population. And the standard deviation, so often what we're trying to do with these confidence intervals on 8.1 and 8.2, we're trying in those 8.1 and 8.2, we're trying to estimate the population mean mu, and we make an interval to do that. Instead of just guessing one point, we say we think the mu is in between this lower limit or lower level and upper limit or upper level. And so we try to give it an interval. And then we have confidence levels and all that stuff for that. But in the real, more practically, I should say, in practice. So in practice, or maybe we should say the real world, if we're looking for mu, right, if we're looking for the population mean, and we can't find that, right, we're trying to estimate that because it's too hard to find, we normally, along with not knowing the population mean, we normally do not know sigma, which is the population standard deviation, right? If the population is so huge, like all males in the world, too huge to find our mu, our population mean, it's probably also too large to find our population standard deviation. So very often the sigma is something we don't know. Now in 8.1 we did know sigma, our standard deviation for population, so we had a formula for that. Now in 8.2 is an example where we don't know what sigma is. So let's start that off by saying, so if you don't know what sigma is, we do the next best thing. Think, not think. Next best thing. So if you don't know the population standard deviation, the next best thing is to use the sample standard deviation. So once again, let's get our notation down. Sigma is the population standard deviation, whereas, I guess I'll make this red, S is the symbol for our sample standard deviation. Okay, so that's our new variable. S represents the standard deviation for the sample, and because it's a sample, a finite sample size n, we can figure out the standard deviation for that. We definitely can figure that out, right? Just like we could figure out our sample mean, x bar. Okay, so this formula up here takes a little turn, and you can see there's some parts that we don't know now. We still know x bar, right? Sample mean minus mu, which is actually, it's going to be the mean. It's actually going to be the mean of the sample means, but it turns out that's by using the central limit theorem. It's just the population mean. I'm sorry, let's see. It's the, what is this? This is the mean of the sample means. And so anyhow, once we have that, then we divide it by this piece right here. But remember, in 8.2, we don't have sigma. We're going to have S instead, which is our sample, standard deviation. So that gets divided by the square root of n. And this new distribution is not the same as the old distribution. This is now going to be called a t value instead of a z value. And there's some real differences between them. One thing is that our z values, our z score makes a normal curve, and we also can, it gives us a standard normal using z scores, right, with the 0 as the mean. Whereas our t values, let me write some notes about the t distribution. So this is called the t distribution. The t distribution, because of this s value, it's not the population standard deviation, which is a constant one number. It's a sample, and every sample that you take, you get a different little s, right? You get a different standard deviation. So let's write some stuff down. Since s varies, from sample to sample, we no longer have a normal distribution. Now, no longer having a normal distribution, that's a real problem. And the thing about the t distribution is it is symmetrical. It does look normal, but it's a little flatter than our normal distribution, like, for instance, the z distribution. Okay, so we have to get around that. So we give a new name, and this new name is a t distribution. the t-distribution uses the sample sample standard deviation S, so it has a greater variance. And so the fact that it has a greater variance, it causes the distribution to be flatter and not as high as a normal distribution. It has a greater variance, so it's spread out a little more. But I want to say, however, as the sample size gets larger, gets larger. Now there's something I gotta define here. So n is the sample size, right? There's something called degrees of freedom. And degrees of freedom is just going to be your sample size minus 1. So, and degrees of freedom is something, it's part of our chart on our distribution. In fact, maybe I'll show that to you right now really quick. These are the degrees of freedom right over here. And degrees of freedom just is equal to sample size minus 1. That's where that comes from. Okay, so we come back down here. I've got my degrees of freedom. So back here, so it has a greater variance. However, as the sample size gets larger or increases, the t distribution becomes very, very close to a normal distribution. And let's take a look at this chart here. I think this is important to kind of break this down. It kind of helps us see it a little bit. First of all, some real important pieces that we need to see here is that when you look up z-values, we're talking about the area to the right with a t distribution. Whereas so far with the z-values, it was always area to the left, right? It always gave you area to the left, correct? Now in this case, it's area to the right. Now this table is used in a little bit of a different way. Let's see. So we're still trying to find critical values with this table, right? So for instance, if we were trying to find, and now this picture is not drawn to scale, but I'm just going to, since I don't have a lot of space, I'm going to go ahead and use this one right here. Let's say that we're trying to find a 90, let's make the numbers nice, a 90% confidence interval. Well, that would mean, and by the way, this notation should say half of alpha. But anyways, if you want a 90% confidence interval, what is 1 minus 0.90? That's 0.10. And you divide that by 2, and that gives us 0.05. So my point is, if you're looking for a 90% confidence interval, the tail, notice it says this stuff is the area in the right tail. Well, the area in this right tail for a 90% confidence interval, right, has to be 0.05. So you would be looking right there. Right? That's the area to the right of the tail for a 90% confidence interval is like 5 cents because, right, 0.05 is over here, and also in this tail over here, we also have 0.05, right? So we had to split that 10% up into the two tails, but we're only concerned about this right tail. So this is considered half of alpha, okay? Something that makes this easier to deal with so you don't have to really split that up every time. Notice that, once again, 90% confidence interval means 1 minus 90 is 10. If you cut 10 in half, you have 0.05. But instead of doing it that way, you could actually, let's look all the way down here in the same column, and it is just going to tell us 90% confidence level, okay? So all you have to do is look down here for the confidence levels, right? Look down here for the confidence level and then go up. The other thing you have to do that's different on this on these t-distributions is this actually represents many t-distributions. This is a t-distribution right here where the sample size was 2, and remember this is the degree of freedom. 2 minus 1 would be given 1. So that's a t-distribution. And this t-distribution has a degree of freedom, and it must have come from a sample size of 15 because the degree of freedom is 15 minus 1 gives us 14. Oops, I just went the wrong way. There we go. Gives us 14. And so this would be an example of a t-distribution. And if we went further about this, that would be the critical value for a t-distribution as 14 degrees of freedom. And we're looking for right tail 0.05, but even better yet, a confidence level of 90%. Okay. So that's how you use this chart. It's definitely a different setup, differently than our Z table. So you got to be careful with that. Something else to realize is that when the degrees of freedom are low, and this means the sample size is low, this t-distribution is not close enough to a normal distribution. But as we move down with more and more sample size, which gives us a bigger degree of freedom, the closer these distributions start getting closer and closer to our approximate standard normal curve, just like z-scores. In fact, you could even see it if you have a sample size or degrees of freedom of 200, which means your sample size was 201. Anything bigger than that, anything bigger than a sample size of 201, we just go ahead and use what? This, which is exactly our z values. So that would be our critical values from the z table. Okay, so there's definitely a connection. This t-distribution is not normal, but as it is close to normal, and as we get above 200 degrees of freedom, we just say, we're just going to use our normal z critical values because it's that close. Okay, so that's something to realize. Okay, and that brings up some information here that I probably should say something about, and that would be some rules for if you can't exactly find, because look, they start jumping. That's 40, 50, 60. They're not showing every single degree of freedom. And then you get to 100, and then it jumps all the way to 200. So, there's a lot of missing degrees of freedom here. So what's the rules of how to deal with that? Let's see. I think I'm going to zoom in a little bit here so I have a little more space to work. And I want to say bullet point if the desired number, we're talking about degrees of freedom, by the way. If the desired degree of freedom that you're looking for is less than 200, then you're going to use the next smaller number in the table. So what does that mean? That means, so let's say if the desired number is less than 200, use the next smaller number in the table. So if we had, let's say, a degree of freedom was 76, well, we don't have 76 here, we're below 200. Use the next smaller number of 76, and the next smaller number was 60, so you do 60. The next smaller number, use the next smaller number. Okay, and then we also want to say something about if the desired number is let's say, greater than 200, just use the z-values, where are those on this table? Once again, once you're above 200, you just use that row, which is just identical, which are just z-values, okay? All right, so that's my little run through of this before we actually do some problems. Let me get rid of some of this stuff so I can actually use this table when we get to that time. So let's move on up. Yeah, we'll get to our formulas. I think at the beginning they're just finding critical values, so just kind of getting used to how do you actually use the table, the t distribution. All right, here it is. Find, now remember on 8.2 is, classic 8.2 is when you do not know the sigma, and you know, the notes are helpful in this. Let's just go down here. This says confidence. So this is confidence. I'm going to read this one right here. Confidence interval where standard deviation is known. That's where you know sigma. That's 8.1. This is confidence interval where the standard deviation is unknown. Now, we should say population. Population standard deviation is unknown, so what do we use? We use the little s, and there it is right there, which is the sample standard deviation. Okay, and that is classic 8.2 section. Okay, let's go back. Okay, so find the critical value, and this is, you can tell, another reason why you know it's 8.2 is you've got a t value instead of a z there, right? So find the critical value, t, it's the t value for half alpha, needed to construct a confidence interval of the given level with the given sample size, round answers to 3 decimal places. Okay, so we want a 90% level, a sample size of 6. Well, sample size is 6, and remember that our degrees of freedom are going to be found by taking the sample size minus 1. So we have a sample size of 6, therefore our degrees of freedom would have to be 5. I'm going to circle that. And let's look this up. We got degrees of freedom 5, and we want an 80%, right? 80% confidence level. Let's look that up on our table. Degrees of freedom 5, 80% confidence level. Degrees of freedom 5, right there. And I'm going to go down here and just find the confidence level is 80%, so it's going to be this way. And there it is. Now, what does this mean up here? Well, this just means that the area to the right of the tail, the area in the right tail is 0.10. But that's, don't really have to know that because they tell us 80% confidence level already. So this is our answer, 1.476. I'll go back up here. And so therefore, this is our critical value, is 1.476. And that's for a confidence level, that's for an 80% confidence level. Let's do the next one. The next one says, I want a confidence, whoops, just jumped. I want a confidence. The next one says, I want a confidence level of 95 and a sample size of 10. So degrees of freedom would be 10 minus 1. Degrees of freedom is 9 with a 95% confidence level. Let's look that up. Man, I am getting distracted here. My kids. Anyways, degrees of freedom 9 and confidence level 95. Confidence level 95. Confidence level 95. There it is. Confidence level 95. Let's go up. We said degrees of freedom of 9. Go over. That must have a critical value of 2.262. So using the proper notation and all, it'd be, this is not a z value, it's a t value. T of half that alpha, the area to the right tail, is going to be our critical value, which is 2.262, and that's for a 95% confidence level. Part C. So I'm looking at this. Degrees of freedom must be 26 minus 1. Degrees of freedom must be 25 with a 90% confidence level. 25, 90% confidence level. There's a 90% confidence level. I guess we're going to change it. 90% confidence level. And we're going to go with 25 degrees of freedom, which I already passed up, I believe. And so therefore, our critical value is, and it should be 1.708. 1.708. Let's go up there. Where are we at? Here we are. So T half of alpha is 1.708, and that was for a 90% confidence level. I think I better clean that up because it's going to be hard to see the next couple ones. Okay, good enough. Last critical value that we're looking for is part D. So we're looking for sample size of 12. So degree of freedom is 12 minus 1. Degree of freedom is 11. So we're looking at degree of freedom 11 and sample size is 99.5. 99.5. 99.5 is right there. I said degree of freedom is 11. There's 11 degrees of freedom. And there's our critical value, which is 3.497. 3.497. That was for a 99.5% critical level. Okay, next problem. We are looking for We're looking for a sample size, so it says a sample size of n equals 44 has a sample mean of 55.7 and a sample standard deviation. So notice all the proper variables. This is not sigma. That is a sample standard deviation, so we use little s. Construct a 98% confidence interval for the population mean, okay, mu. Now, I think it'd be a good idea to jump down to this little guy down here and oops, I didn't need to erase that. Anyhow, look down here and kind of break this down a little bit. And I think what I would like to show on this particular part, let's see, thought I had something else I wanted to show with that. That's fine. Anyhow, let's just look at this. We can see the different pieces here. I guess I'll use some different colors. Just like before, right before, we had this margin of error. So we still have that here with this confidence interval. So notice here, we still have this margin of error. Margin of error that we have to capture. And we still have our sample mean. So we have our sample mean minus the margin of error. And we have our sample mean. We have our sample mean plus the margin of error. And that gives us the lower bound of our interval and our upper bound of our interval. All right, the difference between the previous section was instead of our population standard deviation, we have our sample standard deviation, okay? And that's from the sample, so that's much easier to get than a population standard deviation. Okay, let's see if I can reduce this down. Let's go to the problem right there. And what I would like to do is just write down that formula. That formula was, once again, sample mean minus my critical value from the t-distribution times my sample mean divided by the square root of n. That gives us something called the margin of error, right? And we're trying to say that mu is bigger than this, but smaller than, so this gives us an interval. And this is going to be our sample mean now plus the critical value times the standard error, which all comes together to make, once again, our margin of error. Okay. Okay, so some of the things we're going to need here is, let's see, I'm going to need some of this information. Well, we can see that we have an n value of 44, so that means our degrees of freedom is 44 minus 1 must be 43. That's important, and we have a 98% confidence level. We need to come up with a t-value. And we can do that by using this information right here, right? 98% confidence level at 43 degrees of freedom. So we have our 98% confidence level, right? Was it 98? Yeah. 98% confidence levels right here. And we have our 43 degrees of freedom. So there's 40. Remember what it says? If you're under 200, what did it say there? If you're under 200, then use the next smaller number on the table. Well, we want 43, so we're going to have to use 40. Darn it, I went too far again. Okay, so you can see our critical value is going to be 2.423. There's our critical value. So, and that actually is this part of our formula, right? And this part of our formula. So now, next thing I think I want to get is our margin of error. Remember, margin of error is going to be the critical value, then times, it is S over the square root of n. So when we fill this out, our margin of error is going to be our critical value, which you might as well stick with red, which is 2.423. And that's going to be multiplied by our standard error, which happened to be S, our sample standard deviation, which is 9.3, divided by our sample size, or the square root of the sample size. And so then we put this in the calculator and we get approximately 3.3971132. I think we can use 4 decimal places when we do this. So let's use 3.3971 and 3.3971. And now we need the rest of the formula. We need our sample mean, and there it is right there. Sample mean, which is 55.7. And that needs to be subtracted to get the lower bound. And then this piece is our sample mean again, which is 55.7, and that mean needs to be added to the margin of error to get our upper bound. So when we do this, we end up getting, 52.3029. And we do this calculation, and we get 59.0971. Does it say to round it to something? I don't know. It doesn't say it here. So you can write in whatever level of accuracy you want. I think for some reason they dropped it down to tenths. So this would just be 52.3 is the lower bound. So mu is greater than 52.3 and mu is less than, round it, 59.1. And this is for what? This is for a 98% confidence, low battery, confidence level. Okay, I gotta hurry, battery's dropping out on me here. So now let's finish this one up. This question says, if the sample size were 58, the battery's dropping and so am I. Let's see, this problem had a sample size of 44. And so they're saying if the sample size was larger, would the confidence interval be narrower or wider? So if the sample size is larger, we can make this confidence interval tighter or narrower because you've got, more sample, more data. So more data means you could tighten up that confidence interval. So this would just be narrower. And that is it for the assignment side of ALEKS on 8.2. I've got one more problem to do on the interactive side. I hope that little mini lecture helped clarify some things for you, and I hope everybody's doing great. Take care and continue to study and take that test. Take care. Bye.